Hello all, welcome to my channel. I'm back with another video. In this video, we will be going through some of the performance tuning techniques for Delta Lake. So let's get started. Before we discuss the techniques that are there for Delta Lake's performance optimization, first thing is why we need this. The reason we need this is over time when we have a lake house built on a Delta Lake, there will be a lot of we will be doing a lot of DML operations like insert, delete, and update, and those are handled differently uh, in Delta or in general in any lakehouse solutions. So those are not actual file operations; they are metadata operations that has to be later on combined. For example, when we delete something, there is a deletion vector that gets created. The file is not, the row from the file is not deleted. Well, while reading, we merge the deletion vector with the actual file. So over the time, it needs maintenance, and we need to clean up or we need to do a housekeeping so that the files are in order, not fragmented and not bloated. So that's why we need a regular maintenance, and for doing that, we have different techniques that we can use. So in general, if I categorize things in two I will say blocks maybe. So delta table management can be categorized in uh, two rewrites. One is logical rewrite, another one is physical rewrite. And when I say rewrite, the rewrite of the data files, not of the files once it is written. I mean, once it is written, then if we are rewriting, then we call it a physical rewrite. But if we don't do that, then we are saying it's a logical rewrite. And that's where this distinction happens. So logical rewrite has two strategies. One is partitioning, another one is liquid clustering. And for physical rewrites, we have optimize, ZORDER, and vacuum. So let's see each of them in detail. So what is partitioning? So partitioning is a way for dividing our data into folder or directories based on the values of one or more columns. So let's say if we want to uh, uh, based on the query pattern that we have. Let's say we have a use case that we are running a query on a filter on certain partition. Let's say we want to filter on generally we all the queries will have means if our use case is that all the queries that we are running against the table is queried based on a country. So in that case, definitely we will like to partition our data based on a country folder so that when we issue a query, it's only the files or folders which are relevant, which are tagged for country called USA will be picked up. And we can skip all the other folders. We don't need to query that. That's why partitioning helps in the read performance as well as it also helps us in write performance because we will have different folders and only the files folders are touched where we want to write the data into, but that is very minimal. But read performance is very much improved if we use a partitioning scheme. uh, so to do the partitioning we have to beforehand know on which columns we our query pattern is, and based on that we do the partitioning so that we can leverage uh, the the partitioning scheme for skipping the data that we have. And we can do the partitioning on multi columns as well. So we can have not only partition based on, let's say in this case, let's say on the country, we can also say the partitioning scheme can be let's say continent, country, and then let's say county. So continent is whether it is Asia, it is US, it is North America, South America, stuff like that. And then we have country like USA, Saudi Arabia, India, China. So that way we have sub country based partitioning, and then we have sub partitioning in the countries. Let's say if US we can partition based on county, in India we can partition based on states. So there are different multi column or I will say hierarchical uh, partitioning can be done. But the thing is when we are doing multi-column partitioning, we should be partitioning the uh, our partitioning scheme should be such that the lowest cardinality column comes first. Because, for example, if let's say continent, so continent can be, let's say in the whole world there are 7 continents and there are 192 countries. So if we want to skip a whole continent, if we partition based on continent first, then it will skip more efficiently rather than if we first partition by country and then by continent. So that's doesn't make sense as well logically. So ideally we should be placing the low cardinality columns first, and then increasing order of the cardinality we should place other columns. And how we do it, we say df dot let's say if we are writing in delta format, then we say partition by and give the column names and we save it, and that's how the partitioning scheme works. So this was for the partitioning. Then we have liquid clustering. So there is a challenge with partitioning scheme in here. So once we have written, let's say our query pattern initially was that we were querying or filtering data more on the country, but later on the patterns changed and we are not querying more on that country part. We are, let's say, uh, querying more on some other dimensions. So this physical format that we have already written will not be sufficient enough. If we have to change the partitioning scheme, we'll have to rewrite the whole thing. We'll have to drop the partition and recreate the new partition so that it works. To help work with this, Delta implements a new clustering technology, which is called liquid clustering. And it is replacement of the partitioning scheme that we saw earlier. So instead of creating rigid subdirectories or folders, we define the clustering keys, and what Delta will do is it will store metadata related to the files that are there, and they will not place files physically in different folders. They will just store metadata, and then based on the metadata, that partitioning scheme is fixed, or not fixed, it's changed or updated in real time or in subsequent operations. So the physical file structure remains flat. Like, we will not have any folders. We will have all the files present on a table in a single folder. Everything will be one place, but the logs, the delta log folder will have metadata related to those files, which treats them as a what you call subdirectory or directory, whatever we want to call it. It will treat them as that, and that the indexing will happen from there, and that's how it skips the files as well. So if you see the partitioning scheme in, let's say this is for the partitioning. So if you see sales data, we have region, east, north, south, and west, and inside that the files related to these regions are placed. So this is a physical data. But let's say if the query engine searches on the year, so here, because there is no partitioning based on year, it will have to scan everything. And if we want to have this mechanism, like we want to filter data on every year, then we will have to rewrite this whole data in partitioning scheme with year as a folder. But in case of liquid clustering, because this information like region is equal to north that we have said, it is present in delta log, not on the files. The files are as flat as it is. So if we have to change the clustering from, let's say, north to, let's say, from sorry, region to the year column, then we just have to update the delta log that is there, and then files will remain as it is, and then we will be able to query the data. So that's how this liquid clustering works. It has a concept of incremental clustering, which is nothing but instead of rewriting the whole file or rewriting the whole cluster, it is built on the concept of Z cubes. A Z cube is a group of files produced by same optimize. So whenever we run an optimize job, it will create a Z cube ID, and all the files will be tagged with that. And when the next time when we'll see a new file or unoptimized file, it will do. I mean, the delta will be able to distinguish between the optimized and the non-optimized files, and that will only create Z queues for the new files, and hence it is faster. And also when we need to change, we can just rewrite the whole uh, delta logs metadata, so that we have a new scheme that we want. So that's how this all liquid clustering works with. And also liquid clustering is a table property. It has to be enabled when we create the table. So once we have, let's say, once we have created it, then only we can say, if we want to do it on the fly as like save as table, it will not work. So we will have to create the table separately, define the clustering key, and then we insert into the data. That's how it will work. So that is one thing that has to note. And difference between partitioning and liquid clustering is the structure of partitioning scheme is very static, while liquid clustering it is dynamic. Management is manual. Liquid clustering happens automatically when we write. Query optimization is predefined based on the partition column, but it is adapted to the query patterns. Like today we are querying on area, tomorrow we are querying on year. It works smoothly. Flexibility is limited to predefined columns in partitioning, but liquid clustering we can adapt as well. And If we have predictable and stable queries, we can go ahead with partitioning scheme. But if we have dynamic and ad hoc queries, we should go ahead with liquid clustering. So that are the differences between liquid clustering and partitioning. So these were the two logical things where we were rewriting the files in logical sense. Now we will have physical rewrite where we will be actually doing optimizations based on the files that we have. So the example that I gave earlier, that let's say if we have deleted few rows from a file, the file will still have those rows. It will still consume the space that is there in the data. Listen factor will be there, but it will only affect the reads. So if we want to optimize those things, let's say if we want to rewrite the files based on certain conditions, that's where this optimize commands come into picture. So what this optimize command solves is that it will solve the query execution, it will it will decrease the file system overhead, it will also increase the caching behavior. So this is what it does. So Delta Lake's optimize command is uses the bin pack algorithm to co-locates the data or rewrite. When it is writing the data, it will target the size that it has we have provided, and then it will write tables in that the data rewrite the data files in for example, let's say if we have a lot of smaller files, so it will create a bigger file of, let's say, target data size. And let's say if we have bigger files, it can also split them into smaller files as well. So that's what optimize does. And we have option of saying optimize in the table name, and it will optimize the table. And if we have path based tables, then we can say optimize and then delta and then give the table path, and then it will optimize that as well. And we can even optimize based on certain partitions as well. Like for example, instead of doing the partitioning means optimization for all the tables, all the partitions that are there, we can simply say where sales date is good, so it will only touch the files which are of this date. So this is how we have optimized command, and we can also combine it with zorder that we will see in the later video. Then we have an auto optimize. So this is a table property that we can write so that what it happens is whenever we have time, I mean whenever we believe, it will automatically do the optimization while writing the doing the write system. So it is something which is balance between whether we want write performance or whether we want read performance. So while we have enabled this thing, while during the write itself the optimization will happen so that the reads will be faster. But the actual optimize command which we have there, we have the writes as faster and reads will be slower unless we run the optimize command. So that is something uh, that will happen at runtime itself. So this is something we can give it as a table property. Then we have Z ordering. So Z ordering is a technique which tries to co-locate the related data files in one place. So it is uh, for example, if we have three data files and all those three data files belongs to the, let's say, if we have random location, then what will happen is that similar data will be present in three different files. If we co-locate by job order, so all those related data will be placed in one single file so that we can skip the other two files when we are doing a read or write. So IO number of IOs that we'll have to do, file IO will be reduced. So that is what Z ordering does. And by default now, with newer versions of Databricks runtime, the optimized Z order uses the Hilbert space filling curve. So there are two different space filling mechanisms which Z ordering does. Any optimize with Z or means optimize command can be used with Z ordering as well as Hilbert curve, but by default it uses the Hilbert space filling curves. So the way it does it, that for example in case of Z order, we go diagonally in a sense while choosing the files. We follow this order, which is a kind of a Z, and that's why the name is Z. Like we are creating multiple Z orders. But in case of Hilbert curve, we always keep 90-degree turn. Uh, the turn can be in any direction, but it's generally decided clockwise. So we make that a turn and then find the space filling curve so that the space will be filled based on that. So in a sense, it will happen that the block 1 and block 2 are closer, so they will be placed together. Then block 3 will be placed, and then block 3 will first, not in one block. In this case, again, we have the same structure, but instead of block 1, block 2, block 3 will be placed first, and then block 4 will be placed first, and then block 3. So that's how the difference is there. But Hilbert curve is more what we call is more space efficient, and it co-locates better than JORDER, and hence it has been made default in case of Databricks. The other thing that to note is optimized JORDER by command has a hard limit of 9 columns. We should be, means if you give more than 9 columns, it will throw an error. But the best practice is to use 3 or lesser columns. We should not go ahead with more than that, because more, if we provide more columns, the optimization that we will get out of optimize is will get reduced. So hence there is no point of going beyond 4 columns, and that's what the Databricks also recommends us to use only 3 columns for jet order. Then we have the vacuum command. So vacuum command, what it does, it will all the files which are not being referenced by any of the metadata logs will be deleted. So for example, let's say we have deleted a file and the metadata also got deleted, but the files will still be present on the table location. So this vacuum command physically deletes the old files that are no longer referenced by the table and are older than the retention period as well. So this vacuum command is to clean up the data. This actually deletes the data, and also it will delete permanently. So there is no way of we going back in time travel and everything. So uh, before running vacuum, we have to ensure that we don't have the data requirement at all. So that is something to be noted, that uh, vacuum does break the time travel capability because it deletes the file physically and we will not be able to go back in time. So this is required for GDPR. Let's say if someone opts out of storing or storing their data, so we will have to run a vacuum for there, and also cost management is one other case that we have to uh, take care in case of vacuum. And also vacuum affects other operations as well. For example, uh, when we are running a vacuum command, select queries does work because there is a delta snapshot type listen works in there. We can also write, we can also do a write operations, but we might have a conflict in there because delta follows optimistic concurrency. So it can cause one of the jobs to fail, but delta has an automatic retry. So it will retry and it will succeed. So that is something to be noted, that in case of writes, we might have a failure and retry will happen. Now we run this command is we say vacuum table name, and dry run will tell us which files will be deleted, but the actual deletion will not happen. And then we can actually run this from Spark setting that's retention during the check is set to false, and then we can plan. So this is how uh, we can run vacuum command from different places. And also retention period for testing purpose also we can set it, do the cleanup and then unset it. So that's how we can test few things in vacuum. uh, so these were 3 physical rewrite options that we have, which is optimize, JORDER, and vacuum commands. And once we have these things, like if you see Delta Lake Management feature path, so Delta Management has 2 concepts like partitioning and liquid clustering. With partitioning, we can run optimize, we can run JORDER, we can run vacuum. But with liquid clustering, there is only 2 options. Either we can run vacuum, optimize, and vacuum. There is no concept of JORDER with liquid clustering because there is no partition involved in there, and our files will be as flat as possible. So guidelines wise, design tables with partitioned on low coordinating columns, run optimize JORDER and vacuum on a schedule on new partitions, and create your own. And this is only for Databricks specific, where we have liquid clustering, so we can enable that and schedule a nightly or weekly job to optimize the tables. And so we can say that nightly we can optimize and weekly we can do a vacuum. So that is how it will happen. And there is a concept of predictive optimization for Unity maintenance classes. So we can set this feature. We can enable this feature on a table level, and Databricks will automatically identify the tables that would benefit from maintenance, and they will do the queues those operations to be run, and it will run at a given time, and then it will do an incremental clustering. So this is one feature which is available in Databricks Unity Catalog managed tables, and then this will help us in uh, keeping things in place without us having to worry about this. So this is one feature that we can uh, think of using it. So yeah, that was it for this video. Hope this was useful. And if you found this video useful or you find my content useful, do share and support the channel. Thanks. Have a nice day.